pull Google Meet over. Present. Screen 1. There we go. There we go. Free fall motion. Okay. So, free fall. What is free fall? How is it different than gravity? That's our goal to solve for today. Okay. I'm going to turn off one leg. So, to start off, are weight and mass the same?
No.
Do we use them as the same? Right? This is my weight, this is my mass. Do we? If I tell you to go weigh this, and you put it on the scale, what does the scale tell you? Tell you it's mass. Right? So should I say go weigh it? Probably not. I should say go get its mass. Right? So are weight and mass the same? No. But what is the difference then? Yeah. Say that one more time. Mass, that's kind of like volume. I see what you're going though. You're on the right track. Yes. Weight and mass. So the difference is mass is how much matter you have. Okay? Mass is the amount of matter, right? How much matter is right here. Where weight is dependent on gravity. Okay? Weight is dependent on gravity. So that's the difference. Okay? Mass. So if we think about this, let's say we go to the moon, right? It's always a goal. We go to the moon. Will you have the same mass on the moon? Will you have the same mass on the moon?
Yes.
Yes. But weight, no. Why? There's less gravity on the moon. Okay? So your mass will not change. You will be you. But your weight will definitely change a lot. Right? Because the moon doesn't have that much gravity. Okay? All right. I would just focus on bold if I was writing this down. Okay. Very good. All right. Now weight. So what is weight? All right. Weight has an equation, and that equation is simply Newton's second law. All right. So the equation is weight is equal to mass times gravity. So weight is equal to mass times gravity. Okay, so real quick, if weight is a force, what unit do we use for forces? Newtons, right? So the unit for weight is Newton. What's the unit for mass? Kilograms. And the unit for gravity, what was that? Ooh, it was acceleration. Okay. So those are our 3 units. Okay. So if we, on Earth, weight is equal to mass times the acceleration due to gravity, which we already know. You don't need to write that. We should know that. We got that. We got that. What is the weight of a 1 kilogram book? Cameron, can you see this over here with the sheet up? You can? Okay. What is the weight of a 1 kilogram book on Earth? Well, if we check this out, well, its mass is 1. What is gravity on Earth?
-9.81.
-9.81. Okay. Now, in this case, yes. Yeah, we'll leave that. All right. So, what would the weight be? -9.81, right? Pretty straightforward, right? All right. So that's just saying the force is pulling you down, right? Your weight pulls you down. Okay. All right. So, next one. If somebody weighs 55 kilograms, okay? 55 kilograms. What I want you guys to do is, what would that person's weight be on each of the planets? Try it out. Try it out. Each of those planets, how much would they weigh? Does anybody need a calculator? Now, as we know, acceleration or gravity pulls you down. So, in theory, all these would be negative, right? Okay, so for Earth, I got -539 newtons. Venus, -484 newtons. Mars, -204 newtons. And Neptune, -644 newtons. So based on the different weights, which one has the most gravity? Looking just at the weights, which one has the most gravity? Neptune, right? Neptune. That has the greatest pull. Does that make sense about weight? Pretty good. Okay. So now we get to the free fall. Okay. Free fall. Free fall's definition is the motion of a body when only the force of gravity is acting on the body. That's its definition. So only when the force of gravity is acting on the body. So if I drop this marker right here, I'm not throwing it, I'm just dropping it. What's that in free fall? Was it?
Yeah, only gravity.
I don't know. Your finger.
Okay, if I. What about my finger?
Could be putting some force down on them. There you go.
Like that?
There you go.
Was that in free fall?
I would say so.
Why do you say no? There's this thing called air resistance that affects it. So no, when I drop this marker, it is not in real free fall, which means on Earth, we cannot have anything in true free fall unless we create a vacuum, right? Unless we create a vacuum, which is pretty awesome, actually. Okay. So we know gravity is 9.8. This means that any object will fall in free fall at the same rate. Is that true? We're about to find out. I love this guy's accent.
This is NASA's Space Power Facility in Cleveland, Ohio,
Cleveland,
and it
Ohio.
is the world's biggest vacuum chamber. It's used to test spacecraft in the conditions of outer space, and it does that by pumping out 30 tons of air in this chamber until there are about 2 grams left. And it's got an eccentric construction, which is part of its history. It was built in the 1960s as a nuclear test facility to test nuclear propulsion systems, and that meant that they built it out of aluminium to make the radiation easier to deal with. Aluminium is not the best thing, the strongest material to build a vacuum chamber out of. So they built an outer concrete skin, which is part radiation shielding and part an external pressure vessel, so that this thing can take the force that's present on the outside when it's pumped out to the conditions of outer space. Galileo's experiment was simple. He took a heavy object and a light one, and dropped them at the same time to see which fell fastest. Now in this case, the feathers fell to the ground at a slower rate than the bowling ball because of air resistance. So in order to see the true nature of gravity, we have to remove the air. It takes 3 hours to pump out the 800,000 cubic feet of air from the chamber. Around 2 millitorr lasts 30 minutes. But once it's complete, there's a near perfect vacuum inside.
6104 tank, 10% over. Station 1, go for drop. TCP 30-1, pressure set point at 240 psi. You gotta go for drop. 10, 9, 8, 7, 6, 5, 4, 5, 2, 1, release.
Look at that.
They came down exactly the same.
Look. Exactly the same.
Feathers don't move, nothing. That's just listen.
Isaac Newton was saying that the ball and the feather fall because there's a force pulling them down, gravity. But Einstein imagined the scene very differently.
The happiest thought of his life was this: the reason the bowling ball and feather fall together is because they're not falling. They're standing still. There is no force acting on them at all. He reasoned that if you couldn't see the background, there'd be no way of knowing the ball and the feathers were being accelerated towards the earth.
So if we think about it, we did a similar experiment where we had a golf ball and a ping pong ball. And we dropped them at the same time. Based on air resistance, would they have fallen at the same rate? What?
Because one would be getting so much resistance and the other one would be getting the amount of resistance.
I'm going to turn on the front light. 3, 2, 1. There would be a little bit of a difference based on their size, based on the amount of matter. But in theory, they should drop pretty close to the same. In theory. Okay. So the one thing we need to take into factor is called air resistance. Okay. Air resistance acts in the opposite direction of gravitational force. So what I want you to write is what terminal velocity is. Okay. So terminal velocity is the constant velocity of a falling object when the force of air resistance is equal and opposite to the force of gravity. Holy smokes. Constant velocity of a falling object when the force of air resistance is equal and opposite to the force of gravity. In other words, you're moving really fast at that point. Really, really, really fast. Okay? Okay. There's this guy who tried to reach terminal velocity. A little bit crazy. A little bit crazy, but he almost did it. Equal and opposite to the force of gravity. Yeah, what's up?
So like, from that picture, it says it's like a parachute. So air resistance, isn't that what catches us when we're like using a parachute?
Yeah.
So if there was none, you would just not be, you'd just be flying face first into the ground.
Pretty much. I mean, your body would still cause a little bit of air resistance, but not much at all. That's why when you see skydivers fall, usually their stomach is facing the earth, and they're like this, you know, they're trying to create as much air resistance with their body as they can. All right, so this guy, and this was actually really recent. You might have actually already seen this video. The Red Bull Stratus jump. You guys seen this?
Yeah.
You are restricted. This video is not available in your country. I don't even know what that means. Oh. Why is it blocked in America? America's the greatest country. We're gonna see if there's a secondary video. I can't believe that. That's what I need. It's the space jump. 19 minutes. That's too long. everyone. Oh, this looks promising.
Grammarly can help you write quickly and confidently, so you never have to
Quick
say
ad.
every word.
Oh, this is actually perfect timing. He's really hard to understand. That's why they have subtitles.
That'd be so sick.
Where's it gone?
That would actually be so fun. Just so
Sword and free fall for 5 minutes. Is he falling? That's a great question.
You think he could help as well? Imagine. You should be very excited to jump off my own. My own big outer space and all. He's just floating around. He's still up there to this day. Legend says he's still up there.
Would it be alright if I fast forward a little bit? Just kind of. So he reached Mach 1, so he's going 750 miles per hour right now. 800 miles per hour.
My man is up to my.
That boy's flying.
Eight.
You calling me?
My man is going to eat something. And I'm slowing down.
So speed's really slowing down. Look at his heart rate. Holy smokes. 180 beats per minute.
That's not good.
Oh, he did just jump out into outer space.
That's true. That's true.
It's
It
not
might give you a little
straight
boost of energy.
Blood's probably pumping a little bit.
But he's getting calmer though. He's good. All right, so he's been falling for 3.5 minutes.
He's on that.
Straight falling. There's 4 minutes.
on my knees like it. Really. Any point of sexuality. Oh, my man was 200 miles per hour.
That was actually a pretty cool video. So he reached 830 miles per hour. Can you imagine how fast that actually is?
That boy turned into a jet.
Right? Now, one of the things about air resistance is you might have actually seen people squirrel suit jumping. Have you ever seen the squirrel suits? They jump off cliffs and they fly. Wingsuits.
Oh, yeah.
Those are pretty cool. Based on air resistance, right? Based on air resistance. Okay. So yesterday we talked about orbiting objects, right? We kind of talked about orbiting objects. You don't have to write all this down. You do not have to write all that down. But remember, so an object is always being pulled towards Earth, and if it has a forward direction, it actually creates a parabola, right? It creates a little curve, right? Did we kind of cover that yesterday? Talk about that. Perfect. Now, the same thing happens is if I roll a marker off the table. Oh, there we go. All right, if I roll a marker off the table, right? So if I do that, here's my table. I rolled the marker. What happened was that, right? It didn't fall straight down. All right, there was two forces acted on it. What were the two? Okay, so going down is gravity. What about moving that way? Yeah, force of me pushing, right? So I like to call it the force applied, right? The force applied, put it that way. The force of gravity pushed it down, okay? Now the question is, that marker I rolled, if I rolled it off my countertop and I dropped this marker at the exact same time as that marker rolled, would they hit the ground at the same time?
Let's try it.
So if I rolled one of these markers off, and right when it rolled off, I dropped one, would it fall at the same time? Kind of makes your head hurt a little bit, right? It's like, if one's falling this way and the other falls straight down, will they land at the same time?
They're going down at the same speed, yeah.
Why are they going down at the same speed? What acceleration are they going down at?
Whatever the gravitational pull.
Okay, whatever gravity. So they're both being pulled down in the y direction at negative 9.8 meters per second. So you're saying they are going to hit at the same time?
Yeah, I'm just looking at this.
You're exactly right. You're exactly right. Crazy to think about. Crazy to think about. Right? And these two guys actually did an experiment on it, which we'll see here in a second. Okay? So projectile motion, same thing. What we just talked about, right? Same thing. If somebody shoots a cannon out, all right, if I drop the cannon straight down compared to when it's shot out, they'll land at the same time. Okay? So, last video of the day, last video. These two guys did an experiment from Mythbusters. A bullet, they shot a bullet, and they dropped a bullet at the same time. Which one would land first? That's a lot louder video.
What you got there? This is a good one. Picture two bullets, each exactly the same distance from the ground, each released at the exact same second, except one bullet is dropped to the ground, the other is fired from a gun. The classic physics thought experiment states that both bullets will hit the ground at the same time.
Based on what theory?
Based on the theory that the bullet that's fired from the gun has no wings on it, no lift. Thus, gravity has the same effect on it as it does on the dart bullet, and thus hit the ground simultaneously.
Adam lays down a runway of white paper so the high-speed camera will clearly see and measure both bullets at the same time, in the same place, and in the same shot. All we need now in the drop zone is Jamie's drop rig, so the boys can take a shot at physics history.
All right, you ready to do this for real?
I think we'll hit it on the first shot.
Really?
Oh, yeah.
You never make predictions. That's awesome.
Bullet drop versus fire. In 3, 2, 1. But from 360 feet away, the boys can't see exactly where the fired bullet landed.
Let's go see where it hit.
So Adam takes a one-wheeled ride down the room to check out the drop zone. Wow. And the results are simply ripping.
Can't get much closer than that. Ugh. I can't wait to see the high speed.
Adam analyzes the high speed and crunches the numbers.
3677 minus 3915 equals 238 divided by 6.
Dude, the difference is 39.6 milliseconds.
Which means it's less than a human eye can make out.
So after days of brain-teasing tests, the Mythbusters can claim a world first for themselves. And a victory for physics.
Let me put 39.6 milliseconds into some perspective for you. When you go to the movies and watch a projected celluloid film on the screen, you know that that film's made up of individual images, right? What you might not have known is that it takes 24 of those per second to make up the film that you're watching. So each one is on screen for exactly 1/24th of a second, but you don't notice that because it's faster than your eye can register. Well, that 1/24th of a second is actually longer than 39.6 milliseconds. That's how close those two bullets were.
Crazy stuff. That's wild. But because of gravity, they fall at the same rate. All right. That is all we got today. All right. I'm going to turn on this front light. 3, 2, 1. Back light. 3, 2, 1. So, big takeaway today. We know weight is equal to mass times gravity. Okay? In other words, we said weight was a force. We know mass, and we said gravity was the acceleration, right? Acceleration due to gravity. So weight is essentially Newton's second law. All right? Weight is essentially Newton's second law. All right? Weight and mass, I would know the difference in that. All right? Yeah. You guys have any questions? That is it for our chapter. Okay? That is everything. All right? So from Newton's second law, Newton's first law, third law, to momentum, we kind of covered a decent amount. Do we feel pretty good? All right. So just as you guys kind of know, tomorrow, what I'm planning to do, we're going to have a little review game. All right. Monday, I'll give you guys a review sheet. All right. And honestly, Tuesday, I thought I was going to be Wednesday, but we might have a virtual test. We might have our virtual test because technically you won't be here because of the ACT, but there's still a school day, right? And then Wednesday and Thursday, what we're going to do, we're going to have egg drop. Okay? We're going to have an egg drop where you guys are going to design your experiment and analyze how to decrease the momentum of the egg falling down. Pretty clever
What are you
stuff.
talking about?
So what?
What are you talking about?
The egg drop.
Egg drop?
Egg drop.
We're doing an egg drop?
Oh, so for Tuesday, are we actually gonna have to get on Google Meets and stuff like that, or is it just gonna be like
It's just like videos or assignments. Yeah. I mean, I probably won't make a Google Meet or a Google. Like, there will not be Google Meets.
So this egg drop is to make the egg not break, yeah?
Correct. I mean, that'd be the goal. I mean, I could just drop an egg and have it break. That would be pretty easy. All right. So we'll probably drop them from the atrium. See how it falls. It is pretty far. All right. So anyway, guys, you got about 2-3 minutes left. If you guys got no questions, I hope you guys have a great day. Tomorrow's Friday already. Crazy stuff. All right.
You're changing your last name to Floyd?
All right.
You don't think I want to go?
850 miles per hour. That is 850. Yeah. So that. So he was traveling. Wow. Okay, he was traveling. So he traveled a mile every 4 seconds. Every 4 seconds he traveled a mile.
Oh, yeah.
That is a lot.
Underneath it, he was